In today's video, we'll understand why general circulation of the atmosphere is needed. Earth does not receive equal heating from the sun. The equatorial regions receive much more solar energy, while the poles receive much less. Because of this imbalance, excess heat builds up near the equator and a heat deficit exists near the poles. To balance this difference, the atmosphere continuously transfers heat from lower latitudes toward higher latitudes. This large-scale movement of air around the Earth is known as general circulation of the atmosphere. On Earth, high and low pressure zones form into belts due to two main factors: solar heating and the Earth's rotation. These pressure belts control the movement of global winds and form the basis of the Earth's general circulation. There are four main pressure belts in each hemisphere: the equatorial low, the subtropical high, the subpolar low, and the polar high pressure belt. Each pressure belt is associated with a particular type of weather depending on whether air is rising or sinking. Rising air generally produces cloudy and rainy weather, while sinking air leads to clear, dry, and stable conditions. We will now discuss each pressure belts and how cells are formed. Equatorial low pressure belt. Near the equator, the sun's rays are most intense, heating the surface strongly. Warm moist air rises vertically due to convection, creating a permanent belt of low pressure called the Intertropical Convergence Zone, or ITCZ. This region is associated with towering cumulonimbus clouds, heavy rainfall and thunderstorms. As the air rises, it cools and spreads outward near the tropopause, diverging poleward in both hemispheres at high altitude. Around 30 degrees north and south, the air becomes cooler and denser and begins to sink, forming the subtropical high-pressure belts. The sinking air warms and dries as it descends, creating clear skies and stable weather conditions. Near the surface, this air flows back toward the equator because air moved from high pressure to low pressure. Because Earth is rotating, the Coriolis effect deflects these surface winds. In the northern hemisphere they become the northeast trade winds, and in the southern hemisphere they become the southeast trade winds. These trade winds converge again near the ITCZ, forcing air to rise once more and completing a continuous circulation loop known as the Hadley cell. The Hadley cell extends from the equator to about 30 degrees latitude, with rising air near 0 degrees, poleward flow near the tropopause, sinking air at 30 degrees, and return surface flow as the trade winds. But here is a catch. The trade winds converge but never collide. Because till they reach approximately 5 degrees latitude north and south, they are already so warmed up that they rise. Therefore, a region is formed near the equator in which there are very calm surface winds called doldrums. Now we will talk about the other, low pressure belt, called the subpolar low pressure belt. This is a dynamic belt, which means that this is forming due to Earth's rotation, and not due to direct heating or cooling, like equatorial low pressure belt. Around 60 degrees latitude, warm westerlies from lower latitudes meet cold polar easterlies from the polar regions. Due to Earth's rotation, these winds converge in a region known as the subpolar low pressure belt. As the lighter warm air encounters the denser cold air, it is forced to rise upward. Does this picture make you think of something? If you guessed fronts, you are absolutely correct, because this is where the polar front is born. Around 60 degrees latitude, warm westerlies collide with cold polar easterlies. The lighter warm air is forced to rise over the denser cold air, creating a belt of low pressure. The result? Clouds, storms, cyclones and some of the most dynamic weather systems on the planet. The story doesn't end with rising air from subpolar low pressure belt. As this warm air reaches the tropopause, unable to rise any further, it spreads out and splits into two branches. One branch flows toward the poles, while the other turns back toward the equator. The branch that moves poleward toward the North Pole. There it cools and descends, completing the polar cell. The second branch that moves equatorward toward 30 degrees north. There it descends over the subtropical high and completes the feral cell. Surface winds from both cells then return toward the subpolar low, maintaining the circulation. Now, we will discuss the high pressure belts. Subtropical high pressure belt. Around 30 degrees north and south, air converges from both sides in the upper atmosphere. One branch originates from the equator, while the other originates from the subpolar low pressure belt. As the air cools and becomes denser, it sinks toward the surface. This accumulation of descending air creates the subtropical high-pressure belt, also known as the horse latitudes. This region is famous for its calm winds and clear skies caused by sinking air. During the age of sailing ships, vessels could become stranded here for days or even weeks because there wasn't enough wind to move them. According to a popular legend, ships carrying horses sometimes ran short of water while trapped in these calm conditions, and some horses were thrown overboard to conserve supplies. Whether the story is entirely true or not, the name, horse latitudes, has remained associated with this calm high-pressure belt around 30 degrees north. Now, coming back to subtropical high-pressure belt. Because winds move from high pressure to low pressure, the winds on the surface moved from subtropical high-pressure belt to subpolar low-pressure belt. Due to Coriolis force, those winds are deflected towards right in northern hemisphere and towards left in southern hemisphere. They travel from west towards east, hence they are named westerlies or prevailing westerlies. The westerlies are generally much stronger in the southern hemisphere than in the northern hemisphere. This is because the southern hemisphere contains vast oceans and very little land between 30 degrees south and 60 degrees south. With fewer mountains, continents, and surface obstacles to slow them down, the winds can flow almost uninterrupted around the globe. As a result, the westerlies become stronger and more persistent than their northern hemisphere counterparts. These powerful winds are so famous that sailors gave them special names. The roaring 40s around 40 degrees south, the furious 50s around 50 degrees south, and the crying 60s, also called screaming or shrieking 60s, around 60 degrees south. The names reflect the increasing strength and intensity of the winds as you move closer to Antarctica. Now, we will discuss about the last pressure belt, the polar high pressure belt. At the North Pole, the surface receives very little solar heating throughout the year. The air remains extremely cold, dense, and heavy. Because cold air is denser than warm air, it tends to sink toward the Earth's surface. Also, air that rose from subpolar low pressure belt descends here. This continuous sinking of cold air creates a region of high pressure, known as the polar high pressure belt. From this high pressure region, air flows toward the subpolar low pressure belt at 60 degrees north and south. As it moves southward, the Coriolis force deflects the air to the right, producing the polar easterlies. Now that we've understood the global circulation system, the pressure belts, winds, and circulation cells, let's see what weather phenomena these circulation patterns create. The atmosphere doesn't just move air around, it produces powerful features such as jet streams, cyclones, anticyclones, monsoons, and frontal systems that influence weather across the globe. We'll just do a quick run through about them, and if you want a detailed video like this on these topics, or any other topics, you can comment down below or join our WhatsApp community, or our WhatsApp channel, and you can connect with us directly. Now that we understand the global circulation cells and pressure belts, we can finally see how jet streams are formed. Just below the tropopause, the boundaries between these circulation cells become zones of strong temperature and pressure contrast. Between the Hadley cell and the Ferrel cell near 30 degrees latitude, upper-level air moving poleward accelerates eastward, forming the subtropical jet stream. And near 60 degrees latitude, cold polar air collides with warmer mid-latitude air along the polar front. This creates an even steeper temperature gradient and a very strong pressure gradient force. As a result, extremely fast upper-level winds develop, forming the polar front jet stream. So jet streams are essentially the atmosphere's high-speed wind corridors created by global circulation and sharp temperature contrasts. Tropical cyclones usually form between about 5 degrees and 20 degrees latitude north and south of the equator over warm ocean waters. Temperate cyclones, also called extratropical cyclones, form farther away from the equator between about 30 degrees and 60 degrees latitude near the polar front. They develop where warm tropical air meets cold polar air. The strong temperature contrast creates instability and low pressure. Air spirals inward and rises, forming clouds, rainfall, warm fronts, and cold fronts. These cyclones are cold core systems and are strongly associated with frontal weather and the polar front jet stream. Till now, we discussed global circulation assuming the sun is directly over the equator. But in reality, the sun's direct heating zone shifts north and south during the year because of Earth's tilt. As this heating zone shifts, the ITCZ, the belt of low pressure and rising air near the equator, also shifts. During summer in the northern hemisphere, the ITCZ shifts northward toward India. This creates a strong low pressure region over the Indian subcontinent. So moist winds from the Indian Ocean flow toward India, producing the southwest monsoon. During winter, the ITCZ shifts southward again. The land cools faster, high pressure develops over India, and dry winds blow from land toward the sea as the northeast monsoon. So the seasonal shifting of the sun and the ITCZ helps reverse the wind direction and drives the Indian monsoon system. Here's a quick summary of Earth's general circulation. Unequal heating between the equator and poles creates pressure differences and global wind movement. This forms the three circulation cells, Hadley cell, Ferrel cell, and polar cell. These cells create the major wind belts, trade winds, westerlies, and polar easterlies. At the equator, rising warm air forms the ITCZ, while warm and cold air meet near the polar front in mid-latitudes. Near the tropopause, strong temperature contrasts form fast-moving jet streams, the subtropical jet stream and polar front jet stream. Fronts form where different air masses meet, creating cyclones, storms, and changing weather. And seasonal shifting of pressure belts in the ITCZ helps drive the Indian monsoon system.